But for a test object S, what does it parameterize? It's tuples E0 and E1 of elliptic curves over S. And they are in relation by a degree p isogeny. So it's the degree p isogeny over S, like so. And here, defined in this way, it will be in the end the Lean-Mumford sake of the integers, but maybe let's not put so much focus on it. What you often in fact do is you choose some auxiliary level structure which is prime to P, and then you in fact get a representable problem, but never mind. So, and I want to view this over the p-adic integers. So it's defined over Z, but I restrict my attention to the p-adic integers and I want to study the mod p reduction. And so how does the local model come into play? So there's so-called local model diagram. Let me write it here. So at the bottom here is moduli space just defined, and then there's certain cover. And the local model is sitting at the other end of such a correspondence. That we give this names and then explain what these objects are. So here, so first this curly M with the tilde. This parameterizes the same data as our curly M without the tilde does, but you add an isomorphism or more precisely trivialization of the first de Rham homology, first relative de Rham homology of the chain. So, and oops. And this is something, maybe let me call this datum alpha. And there's something you have to prove, but there's always sort of a locally on S, there's normal form. And it looks like this. So it's supposed to be degree p isogeny. So we have a p up here and p down here. And how do we get such a triple? It's by adding somehow using the self-duality of the elliptic curve E1 under the Weyl pairing, and then adding the dual isogeny. You get such a chain, and the first de Rham homology locally always has such a normal form. Okay. And then what is this map phi here? It's simply the forgetful map where it forgets the trivialization. So if I just forget, and I give it a name, forget alpha.
So when you say isomorphic, it means H1 derived is isomorphic to the H1 in the middle, or what?
No, it's somehow shorthand notation for here's E bullet, and I somehow trivialize each of those, and then E0 again connected by the dual isogeny, and
it's a diagram.
It's a diagram. It's a diagram. Yeah.
Okay.
Yeah. So. Okay. And then let me tell you what this local model here is. somehow what this is in the example is somehow dictated by the shape, whatever you get out as a standard form here on the first rank homology. And here you simply parameterize pairs, E0, E1. Then again, you have the chain from upstairs. Like so. Oops. And E0 and E1 are locally direct sums of rank 1. Inside there, and subject to the condition that these diagrams are commute. Okay. So if yes, of course.
I mean, usually these are coarse module spaces for elliptic curves equipped with, say, a generator of cyclic subgroup over the rank, local cyclic, or just a subgroup over the rank.
Of the
p-torsion. So of
the p-torsion.
Yeah. Can you look at a connection with this interpretation? I mean, that's the definition in Katz-Mazur now, the moduli problem. You have to choose some
of this moduli problem here, right?
Yeah, there are force moduli problems, by the way, because you have this gamma 0 and then a bit more structure to get a full moduli problem. No? But I was wondering, since this is very different from the usual formulation you have with the moduli problem, I was trying to figure out which is the relation.
Well, I mean, here this is basically the same. Well, it's formulated differently, but it's a one from Katz-Mazur.
Yeah, exactly. But I was wondering the connection with H1 around. I mean, H1 is the Tate module, so basically it's dual to each other. So basically, that's the same thing as
it's the same
torsion there. But I was wondering, since I don't see quite clearly the connection, I was wondering if there is a way to understand this curly in 0 in 1 in these terms.
Good point. Yeah. I cannot answer.
No problem. I was just asking myself because it's a neutral way to me.
Okay, and so here, if for example, if you look here, if P is invertible on S, then here you just have isomorphism. So E1 determines E0 and vice versa. And so you just get projective space as a projective line. But if P is not invertible in the base, this is something different. It's the shape of this, and maybe I can squeeze it here. What is the map psi here? Somehow the map psi is in a way the interesting map. This is the image of the Hodge filtration. Hodge filtration under this isomorphism alpha. So the Hodge filtration in this case, it gives you locally rank 1, locally direct sum of the rump homology, and it will give you rise to such spaces here. You get a lot of like that.
Can you just clarify? So the model does it parameterize diagrams like this, or does it parameterize just pairs that fit into the diagram?
It parameterizes pairs that fit into the diagram. So the diagram is a condition. Okay, and what properties does this local model diagram have? So the following properties. First, that curly phi, it forgets the trivialization up there. So this is simply torsor under a certain group scheme. And here, let me give it the name curly G. And these are some automorphisms of such chains. So then with this chain here. Okay. Let me just say the name. This here is so-called Ivory group scheme. Okay. Something which is a generic fiber is GO2, and it has this integral structure. This map psi, here, which takes the image of the Hodge filtration. This is I show it smooth by information theory and equivariant under this curly G. And last but not least, here this is somehow the dream case. We have a very, very explicit model. So in particular, the second bullet point, which is maybe somehow the point of key interest, especially the smoothness here, it tells you that in order to understand the singularities arising here in the reduction modulo P, they are locally the same as the singularities that arise here in the reduction modulo P. And in this case, one can also simply just say directly what this is. This here is, you start with a P1 over ZP and you blow up the point in the special fiber. So, So think about this here is something like a surface. It's two-dimensional. It has two directions, an arithmetic one and a metric one, and you blow up the point in the special fiber, and you get an exceptional divisor. And here, the special fiber. Oops. That's a geometric special fiber. It's like two P1s crossing in this. So it's a copy of P1 and another copy of P1 crossing in a single point. Okay. Yeah, this in a way might be somehow the initial example. It's going back to this work of Deline Rappaport and even earlier. And what people thought about a lot is they would like to have a similar story, but for general Schmor varieties, not just for GR2. And what I'm going to do in the rest of my talk, it's not chronological, so I somehow more or less start with the latest stuff and then later come back to other stuff. So and
so sorry,
yeah, sure.
Generically is still a P1.
Right? Generically, it's still a P1, right?
You don't touch it. Okay.
You don't touch it, right? Somehow, then you can consider it's nothing. Okay, so let me now come to local models. And
sorry, I do that.
Yes,
let's listen. So if you are generically still P1, because it's a blow up. Yeah, but the special values of this module space, I mean, it's not necessarily zero.
That's correct, but so it's only so what I mean. The way I like to think about it actually is after quotienting out this curly G action, what you get is a map from this modular space too. And then you have here this local model, and then there's maybe a static quotient, and this map is only smooth. So it somehow doesn't tell you about, it does not speak about the genus of that thing here. This might have other genus.
Okay, but the generic fiber, this should be the same as generic fiber. I mean,
yeah.
The same modular curve.
Yeah,
you may have genus, any genus you want.
Yes, the genus, I don't know. It's there are curves. You can calculate the genus of this series. Yeah, it can any.
I mean, there are the curves of conductor P.
So here I'm only talking about after having performed whatever this is here, you end up with a smooth map, and I'm only talking about the target having generic fiber P1.
Okay, I see.
And this is, of course, we would like, it's a study of that object here, we don't change it at all.
So you are thinking as an end of the J invariant or something like this, or what?
No, it's more, oh yes, I see what you say. Yeah.
It's somehow it's a kind of thing which is invariant under some
integral
pieces. So it looks like C or something.
It's an integral version. Somehow,
yes.
It's a periodic map. Yeah.
Okay, thanks.
Yes. Okay, so let me now come to local models, and so here, straight G is a reductive group over QP. Okay. This curly, which I fixed for the whole talk from now. This curly G is so-called parahoric model over the peak. And so this was defined by Bruyère and Titz in this generality, and whatever it is, think about it as, in this example, it's automorphisms of that lattice chain. Okay? And also, from a Shimura variety, you always get a conjugacy class mu of, so it's a geometric conjugacy class of minuscule co-correctors. Coming from the Hodge co-corrector of the Shimura data. And this also gives you E over QP, the reflex field of mu. So the field of definition where this conjugacy class is defined. And maybe here before writing it, I should explain. So people wanted to have a similar picture in more generality, and they thought about, okay, what could this linear algebra object be on the side? So how can I define this object in first place, and then maybe in second place make the connection? And in a way, this was only clarified around 2014 in a conjecture by Scholze during this book of Scholze and Weinstein. And it states the following. So with these hypotheses set here, with the notation, the conjecture claims existence, there exists a flat projective scheme. And G mu over the ring of integers of the reflex field with reduced special fiber. And okay, now you have to wait a second for the interesting part.
So can I just read?
Yes.
Also, when you start with Shimura, do you consider like Shimura varieties in the sense of shorts, like local Shimura varieties, or is it like a general consideration of Shimura?
No, somehow what I do in my talk, I put everything related to the Shimura side away for now, and only extract the local data and work with this local data.
Okay.
So in application, such a triple here, or in fact just a tuple, because this knows about G.
Yes.
This tuple would come from a global situation, and you would localize at the given prime number P.
Okay.
Mm. Okay, and together with a closed immersion, and closed immersion of what? And let me just write it as a conjecture. Namely, in this book of Scholze-Weinstein, it's about adic geometry, and the characterization is in terms of adic geometry. Namely, it claims the existence of a closed immersion from the associated V sheaf to such an object into, this is the BD1 plus affine Grossmanian for kernel G. Okay. This is literally, and maybe I should fix the generic fiber and extend it. So the generic fiber of this object here, just as in the GL2 case, it's supposed to be the space of parabolics of type mu inside G. And the isomorphism is supposed to extend parabolics inside G of type mu. With the corresponding, one can construct such a fixed isomorphism here. There's somehow natural choice of this. And the claim is that this isomorphism extends to such a closed immersion to such an object here. Okay. Whatever these objects are, let me not focus too much on it. But yes.
Before we forget the focus, can I ask something?
Yes, of course.
But you base change to SPD-OE, but is it defined a priori over SPD, or to be you base change from SPD-ZP?
From SPD-ZP.
Okay.
Right. This object here is defined wherever this curly G is defined. And then we have this extension of ZP.
Yeah.
Which somehow comes in because this might not be defined over ZP. And so what is the remark here? Somehow asking for this reduced special fiber. This reduced special fiber. It's basically equivalent, but let me. It together with flatness, it implies normality. And then from there, one can see, because one knows that on such objects, this process of taking the associated V sheaf is fully faithful, it implies uniqueness of that object. And in fact, there is a bit weaker notion, which implies also uniqueness. It's weakly normal. Also here. Okay. And what whatever this characterization is, but what this conjecture is supposed to tell you is what is this linear algebra object which is supposed to appear on the other side after passing through this process. And what's the theorem about this? So the theorem is simply the conjecture holds. So let me first write the theorem and then say who did what. And more precisely, so that's part one, existence. So there exists a flat projective and weakly normal scheme engineer with such a closed embedding as in the formulation of the conjecture. Okay, and two, there's a geometry part. So in particular, this was done in the PhD thesis of João Lorenzo to separate somehow the conjecture into two parts, an existence part and a geometry part. And this first part doesn't yet imply the full conjecture in the sense that it doesn't talk about reducedness of special fibers. But then there's a geometry part, which says that this object here the special fiber is a geometric special fiber is always reduced. And more, one can say explicitly what it is. And equal to the canonical deperfection of the new admissible locus inside the width vector of inflectorality. Okay, what is going on here? So taking this, so we are supposed to embed it inside such an object. The special fiber here is a V-sheaf associated to the width vector of inflectorality. And then if we, in the end, we would like to have a finite type scheme. And all the stuff inside here is perfect by construction of this object. But there is a way to write down a canonical deperfection. And you end up with a finite type scheme, and this new admissible locus is some explicit portion inside here defined in terms of affine value combinatorics. Yes?
Just another question, sorry.
Yes.
So for modular curves, here you are taking the perfectoid curve, I guess. So the inverse limit of all the P to the N structures. I mean, I don't see any letter structure here, no?
No, I mean, we are somehow, at this point, we forgot about elliptic curves. We are solely on the linear algebra side.
Sure, but if in general, Shimura datum is the datum of a relative group and some open compact subgroup, no?
Yes.
Okay, so since I don't see any open compact subgroup, I'm wondering if you are taking the projective limit of
the open compact subgroup is at P, it's the P points of this guy here. It's an open compact subgroup.
Okay, so it's maximum.
No, not really maximal. It's in the example of GL2, it was upper triangular modulo P.
Okay, but then I have another question.
Yes.
Because in general, if you take these modular curves, you take gamma 0 to the n with n bigger than 1, you never get something.
No, this is also not parahoric. So this is somehow excluded from that theory, unfortunately.
Okay, I see. And how do you exclude this case?
By the
parahoric thing?
Yeah, by the parahoric thing.
Okay.
I mean, these things are somehow upper triangular modulo P, let's say. Okay. The P point of it.
Thank you.
Yeah.
I see. Thank you.
Yeah, that is unfortunate. Somehow, of course, it would be great to have it also for deeper level structures, but the geometry just gets very complicated somehow. Yeah.
Just like that.
Okay. And there's part B, and the sole object is also called Macaulay. Okay. So there's some very nice singularities. Let me talk about the attribution. So one disappeared in joint work with Johannes Amschütz, Ian Gleason, Joao Lorenzo, and myself. And also we prove this to a part, so it's also in the same joint work, except we couldn't treat the following two cases. So p equal to 2, and after extending scalars to the maximal unramified extension, this is an odd unitary group. And or p equal to 3, so somehow wildly ramified unitary group of odd dimension, or G pupil graph. This is a triality for p equal to 3. And these two cases were later handled in a joint paper of Gleason and Lorenzo. So I write each name out once, and then I use abbreviations. And to B, there's space on joint work with Haynes and myself, and then there's a follow-up paper together with Nashmini, Fakudin, Haynes, Lorenzo, and myself. And yet another follow-up paper, so this handles all cases except again those two. Another follow-up paper by Robert Cast and Joao Lorenzo for p equal to 3. And the p equal to 2 case, via completely different methods. This was proven by Schuhu Höhl, Felix Stemmer, and Yu, or p equal to 2. I should say they have a uniform method treating all groups at once, and it's a combinatorial method, which is also quite amazing that you can get this geometric statement from pure Y group combinatorial. Okay. Let's focus out a bit. So it's very nice. So there's a general theory of such objects, but what you miss completely from the picture, from the example, is a moduli interpretation of these objects. So, and of course, this is the way that people got interested in this. And I guess the obvious question is, does there exist a moduli interpretation? Of this guy here. And what are the known examples? So known examples. So there's starting from the PhD work of Ulrich Goertz. It's cases of GLN and it's a symplectic group. And actually some more cases related to restriction of scalars of such groups. Then there's work of Smithling and Lee for orthogonal groups. So, and yeah, like this. But I should say here, so the GLN and the symplectic group examples, this works out nicely. There are moduli descriptions of this. Already here, as far as I'm aware, there are only partial results, fixing some special type of minuscule co-character or treating odd ends and even ends differently. There's further cases people have studied, starting from work of Papas Rappaport, Artsdorf, Strang, and Liu. Maybe I should also add Smithling. Yes, boost. Also partial results in the case of ramified unitary groups, ramified general unitary groups. And somehow, what is the upshot? So there is a modular interpretation for GLN. And then as the group gets more and more complicated, to that moduli description, you add some of further linear algebra conditions, which in the end hopefully force your object that you get in this way to be flat over the integers. This is somehow what you have to make sure. Okay. And yeah, and somehow the more complicated the group is, the more complicated this description is. Yes?
Yeah. Over C, these are PEL varieties, or because
yes, basically, yeah.
They are all
of PEL type.
yes.
Yeah, maybe ignoring some misogynies here. Okay, and what do we do now about this? Okay. Instead of trying to write down the modular interpretation for this here, we first considered a case which in some sense is easier. Namely, we try to write down a candidate for the associated V-sheaf. Okay. And I denote the associated V-sheaf by such a mass BBM. And this is joined again with Lorenzo and then Fiemann and Wittler. So let me also say it's in progress.
So I'm very sorry.
Yes.
So when you write this, like, you consider this functions on analytic Canonic spaces over ZP. I mean, how do you look at this type of here?
Well, what is objective view?
No, I mean, you look at this as like a function on analytic Canonic space, mapping like one P plus
perfected spaces and characteristic
space.
Characteristic P together with a map to the diamond of ZP.
Yeah, okay. Okay.
Which some objects is unroot. Okay, and let me, for simplicity in this talk, let me assume from now that G is split. I'm aware this is not a natural assumption from the Schmorr variety point of view. And we can write down everything in full generality, but for this talk, I would like to assume this. And this also means that the reflex field will just be copied, and I drop it from now from the notation. And let me choose also maximal split torus contained in a Borel subgroup denoted E0. And this conjugacy class of minuscule co-correctors, I then can find a representative with which maps to the given torus. And furthermore, I can also, after conjugacy, assume that it's dominant with respect to the fixed Borel. And then our description is in terms of a Lagrangian formalism. And let me denote by rep curly G. These are representations of curly G on finite 3 ZP modules. Okay, this in hand. So, what is the candidate for the modular description? It's one condition, but for every representation. So, yes. So first, this condition depends on some integer. And let me, for every such representation of this curly G, attach the following integer. The notation is mu max of V, the maximum mu weight inside this curly V. And this is maximum over all characters of the given torus. And then you pair it with your co-character mu. And chi is supposed to be a weight of the generic fiber of this representation. So the generic fiber of the representation is a representation of straight G. And I restrict this representation to the maximal split torus that decomposes into weight spaces. And I take the maximum, and in particular, there are just only finitely many weights, and I take the maximum over all these pairings which appear. And so, what is an example? Let's take a dominant character, and how do I get a representation? So simply by inducing that dominant character from the Borel, and somehow if I want to end up with representation of highest weight this given character, I have to induce from the opposite of the fixed Borel. And I can ask myself, what is the maximum mu weight here? And well, it's simply pairing with mu. So both are arranged to be dominant. So this is some non-negative number. And this is what this computes. And for example, if you look at GLN, and mu is minuscule corresponding to maybe I have r times entry 1 and n minus r times entry 0. Then, the mu max. So for GLN, I have the fundamental representations, which is the ith wedge of the standard representation. This representation is also of this induced form where this character chi has I times the entry 1 and n minus I times entry 0. And then this maximum here is attained by the minimum of the integers r and I. So somehow r is the r from the minuscule mu here, and I is the I wedge. Okay. So it's very, this very explicit. Okay, and then before writing down this candidate for modular interpretation, let me swiftly recall the BD-ROM class at Grossman. So for perfected being perfected over ZP diamond, this parameterizes curly G torsors on So I have the BDM plus string associated to being living over this diamond over ZP. It comes with an untilt, and to this I can associate it the BDRAM plus period group. And I think about this as some fancy version of a disk, together with the trivialization over the puncture disk. So trivialization outside the locus where psi is equal to 0. Okay. No. Okay, then the definition. So we'll define a subfunctor. So bold m equal to g mu prime inside the stick state given by so those trivialized curly G torsors, such that for all representations in inside here, we have one condition, namely, I take this psi inside, oops, giving rise to this divisor here, and raise it to this non-negative integer by my representation. And act on this module. So inside here, what's the condition? Okay, maybe I should add some explanation. What is the explanation? So the first explanation is that this rho star, this is the induced map from a rho is mapped from curly G to this one here. And this formation of these Grassmannians is functorial in the group. It induced for me a map like so. And I can then take the object here and push it forward along this map. I get an object here. And now what are objects here? These are objects inside here are lattices, BD-RAM plus lattices inside, so with a fixed trivialization. But this just means that I view the lattice as living inside somehow the same vector space. Yes?
So is seeking the kernel of the containing map?
Yes.
Okay.
Yeah, it's a kernel of the CEDA map.
Yes, okay.
So may I ask you just
yes.
So your thing, so this row, the rho star is a map from torsors over the current G.
Oh yeah,
to the torsors over GLP.
Let me write. I'm pushing out the torsor along. Oops. And this push out is along row.
And B is any. I mean, this representation you take is beyond one or what?
Oh, it's an algebraic representation on a finite free ZP lattice.
Okay. So B is a finite free ZP lattice.
Right.
Okay.
It's an right. This is also like a GLN over ZP.
Yeah, that's why I was wondering.
That
the notation was different. Okay, thank you.
Yeah. Somehow I don't know. I only writing GLN here, I somehow get confused. Yeah. Okay, so there's a quick remark. Maybe I should say why. So this integer here only depends on the generic fiber of this representation. So this integer doesn't see any integral structure in particular. Okay. Why can it still be that this is the correct object? Because in the end, we want to have some flat moduli space. And in particular, by being flat, it's somehow determined by whatever it is on the generic fiber sitting inside a bigger space somehow. So I need to write down a condition which only depends on the generic fiber. But what does see the integral structure is the fact that I asked rho to be an integrally defined representation. Okay, this highly, I mean, the family of such representations determines this curly G ubiquity somehow by Tanakian formalism. Okay, so there's a remark. Let me name that condition star here, star for the dual representation. So we do. What does this So this here holds for all representations, in particular for the dual representation. And if I plug in here V dual, and rho dual, and I dualize it again, this inclusion swaps, and I get an upper bound. So I get rho, the lower star of E is contained inside psi of mu max curly V dual, and then times this lattice here.
You have a bar for V of V. I don't know, just from the issue.
Yeah. Right, and in particular, what this remark tells you is whatever this subfunctor is, it's somehow a bounded portion of this big space. So okay. Let me write it as a conjecture star, which means I'm fairly certain it should be correct. But we can't prove everything yet. So let's assume there are two assumptions I have to make. The derived group is simply connected. And another assumption, which only matters for non-split groups. So the second assumption that the inertia co-invariance of the fundamental group of G are torsion free, it's automatically, if the first assumption is satisfied, this is automatic for split groups. Okay. So in a way, since I assume the group to be split, and forget about this. But let me write it nevertheless. So there's a version of this conjecture for general groups, but it simply takes more effort to write it down. And the conjecture is that this moduli functor is in fact this local model here. Okay, and there are now two things. So if you think about a moduli interpretation, you would like to have a finite amount of data you write down. And here we are obviously writing down an infinite amount of data. We are testing against all representations. But there is an effective part of the conjecture which exactly tells you, depending on the group and depending on the mu, against which representations you have to check. Okay. And it reproduces examples from the literature. So
sorry, what's the IQ?
Yeah. Sorry?
What does the subscript I mean?
So the fundamental group of G, this is a Galois model and the Galois group, and this I is the inertia subgroup of the Galois group of QP. It's a co-invariance. Okay, what is this proposition? What can we prove so far? So under the assumptions in the conjecture, following things hold. So first, the generic fiber of this object, it's the correct generic fiber in the sense that this is the Schubert variety. So it's a Schubert variety in the generic fiber of Saphan Grossmanian. Maybe let me just write equality here. Both sides are subfunctors of the same ambient thing, and they're just equal to one another. And secondly, we have the following inclusions. So to prove the conjecture, one somehow has to identify the generic and the special fiber of this object. And the special fiber always contains this new admissible locus. And somehow the conjecture claims that this inclusion here is an equality. This we can't prove yet in this generality, but we can show that it's always contained in the so-called new permissible locus in the vector of inflectability. This new permissible locus is a variant of this admissible one, stemming from a time where it wasn't so clear what the special fiber should be, and it turns out it somehow naturally pops out when thinking about these Tanaki descriptions. And in particular, sometimes it's true that the admissible one is equal to the permissible one, and this already implies that the conjecture holds if G is classical. And what I'm somewhat implicit assuming, but let me make it explicit again, that mu is minuscule. So classical means types, Dinkin types A, B, C, D.
If the conjecture is true, will both these inclusions be equalities or just the first one?
Oh, just the first one would be an equality. Yeah, it's known that this permissible locus is in general strictly bigger than this admissible one. Okay. Let me explain an example. And somehow for me, when thinking about this, an instructive example was again this GLN case and the curly G. It's automorphisms of such lattice chains. So it's exactly, and so in the GL2 case, we had such a chain with 3 members, and the GLN case, I had such an N chain. And maybe, so here, each VI is just ZP to the N, and the transition maps here, so ZP to the N, which is VI plus 1. This transition map is given by you put ones, and then there's one P, and then there's 1, and this P is at the I plus first place. I plus first place. Okay. So in particular, if you multiply all these maps together, it's P multiplication again. Oh, no, erase the condition. Okay. Okay. This is so-called Ivahori group scheme, and I take mu again r times 1 and minus r times 0. It's a minuscule co-corrector. And let me, in view of the proposition, let me ignore the generic fiber entirely and only focus on this first inclusion here. Okay. I take curly E. Well, now I look at torsors under such a chain. So what is a torsor? It's just a form of the chain. So the torsor is again an object of such a shape here inside the width vector affine flag writing. Let me also, for simplicity, assume it's an FP point. Doesn't really make any difference. And then we test the condition star in the definition of the moduli problem for well, we now have to construct representations of that curly G, but luckily this is really easy because I can just take automorphism of such a chain and project on a member of the chain, and that is a representation. So this is a forgetful map. Automorphism of a chain is like a tuple of automorphisms with some conditions, and I just project on one member. And I test the condition star for this and its dual representation. Okay. And then what do I get as a condition? So I take my torsor here and push it forward along this here. This is just remembering the ith member here. So I get a condition on EI. And then I have so these conditions will be of the following chain. Okay. And somehow I have to figure out what these exponents here are. So how do I compute these exponents? Generically, this map here is simply an isomorphism, simply because generically all the transition maps in this chains are isomorphisms and nothing happens. So generically, this is the standard representation of GLN, which corresponds to the weight. So this is the standard representation of GLN generically over Q. So after tensoring with QP. And so this corresponds to the weight pi 1 and then 0 and minus 1. Okay. And what is my mu? This is of this form. And so I just compute the maximum pairing. Well, after permutation, it just gives 1 as a max. So here is p to the 1. And what I do here, well, to get this inclusion here, I have to look at the dual representation. The dual representation, so the dual weight will be n minus 1 times 0 and then a negative 1. This is still a dominant one. And then I compute the pairing, but now the max of the pairing is 0. Okay, so here I get p to the 0, or I can just erase it. Okay, So I get lattices EI with this condition here. There's a bit more. So the loan doesn't completely determine the smooth locus. And then next we test this condition for the determinant representation. So I take the highest wedge power of, I again project onto VI and take the highest wedge power. And the dual, one can do a similar computation and see that it forces the highest wedge of EI to be simply the ideal generated by P to the R. Okay. We see the relations between N, R, and I. Oh, yes. N is the dimension of GLN. Okay. Yes. R comes from this minuscule co-corrector. Okay. And I comes from, I'm projecting on the ith member of the lattice chain to get a representation. Okay, so if I is the ith level of the chain. Okay. Yes. And I what you can also see from this here, you somehow have to project onto all the eyes. So then it is independent of R. I mean, what you get? Lambda Pn EI will be equal to P ER. Oh yeah. Okay. It's like in the moduli problem, it like fixes some of the connected component where these things live. Yeah. Somehow the discrete invariant by. And this is you get new admissible locus for GLN. Somehow you can also make the connection to the GL2 example, and the connection is given by there we parameterize locally direct sums of rank 1. And to see this picture, you have to pass to the quotients by this lattice everywhere. So you replace EI by EI modulo. So you have 0, EI modulo P times VI modulo PI, which is then something two-dimensional in the GL2 example. Yeah. So this is somehow how you get back to the initial example. Okay. Let me see what to do. I think well, it depends on you. So what I could do, I think I could prove the first part of the proposition, identifies a generic fiber of the modular coverage. There you can see why this assumption that the derived group is simply connected matters, or I could stop here. You choose. I also see a roof. Yes, okay. Then let's try to give a proof. Proof of proposition 1. You can then also, from this what I sketch here, also somehow see what to do more generally to get an end on the special fiber. So in particular, this hypothetical proposition claims the moduli description of these Schubert varieties. So this let me denote by Schubert variety prime the subfunctor such that this condition star defining this moduli problem holds for all representation rho comma straight V as representations of straight G. Okay. Yeah, it's no integral structure. I just have straight G is a split product of group over 3P, and I have this one condition, and I testify any representation. And what I somehow would like to black box, what always holds is the following inclusion. So this always holds. And it's not hard to see. And what is really to show is the following thing, namely under the condition that the derived group is simply connected. We get that this conversely, this prime version is also contained in this. Okay. This inclusion holds without conditions on G, and the reverse inclusion only holds with this condition. For example, if G is PGL2, this here will be a strict inclusion. And the fact is simply because PGL2 has many representations than SL2. You only get the even symmetric powers of the standard representation. And SL2 has all symmetric powers of the standard. Okay. Okay, so let's denote C completed algebraic closure of QP and BD-RUM plus the BD-RUM ring for C. This abstractly isomorphic to not Galois equivariantly, but abstractly isomorphic to just the power series ring inside. And let's assume we have some dominant co-weight such that after evaluating the dominant co-weight, we lie inside our prime counter. Oops. And what we want to show is that if we have such a co-weight lying in the prime functor, then it will also lie in the other functor. And then there's somehow some trick using some equivariance under some groups, which then gives you the inclusion. So there's a positive loop groups which act on the picture. But this is the essential thing to show here. And just let me, this here is a condition on this new. And let me write out this condition on the new. So the condition on the new is we have psi the mu max of v times BD-RUM plus, in terms of v. Is contained inside mu is a co-corrector of T, and you post-compose it with a representation and evaluate that at psi, and use this as a multiplier for the letters. Okay. And this is supposed to hold for all pairs rho being set here. Okay. So what does this inclusion here means? This means that somehow all psi powers that appear here, they cannot get too large, and too large means they cannot get larger than that number here. Okay. And if you translate this back, it means that the maximal mu weight of V will be less or equal the maximum mu weight of V. And now to get, in the end, we want to get some specific numbers here, enough numbers somehow, and we want to conclude something about this nu, and we apply this to the representations, to the highest weight representations. So for chi, the dominant character, and then for these representations, the left-hand side is simply the pairing, because everything is chosen dominantly with of chi with nu, and this is level equal to pairing of chi with nu. Okay, and mainly for all chi and inside here. Okay, so far we haven't used anything about the group, so this always holds. But if also this equality is always implied if nu is less or equal to mu in the dominance order on co-characters. But for the converse here, this needs the Dirac group to be simply connected. Okay. This is also precisely some of what fails as a PGR example. And this level equal in the dominance order implies that this psi, that this point here lies in the less or equal to mu part of the Grassmannian. And this then with using some equivariance conditions gives us equivalence. Okay. Which then gives you both inclusions and then equality. Let me draw one conclusion from it and then stop. So still the question remains, do we have to test against all representations? And the answer is no. We only have to test against so many representations that from this inequality, we can conclude that inequality. Okay. And this is something one can handle. So namely for any subset of dominant characters, define a variant of that functor where with J in the upper index, it's a subfunctor such that star holds for all representations for all these induced representations with chi. With chi in the given subset. And the corollary is if G, this derived group, is simply connected, then we have that the straight version is equal to the Schubert variety whenever, so for any subset J inside here with the property that generates the rationalization as Q greater equal to 0 monad. Okay. Where does this rationalization come from? Somehow the inequality here produces integers, but this inequality, I mean, it's a perfect pairing between Z lattices, and it doesn't see whether you are just in Z or whether you tensor with Q. There's nothing lost after tensor with Q. But it makes a difference whether you want to generate this monoid as a Z greater equal to 0 monoid or just as a Q greater equal to 0 monoid. Okay. And this here is simply a bit weaker. So any subset which generates this as a Z greater equal to 0 monoid would be okay, but this condition is a bit weaker. And now in particular, coming back to the, of course, you want to connect it with the examples you see in the literature, which people have computed in many cases. And to do this, so in this part here, mu is any co-character, not necessarily minuscule, but later in the application, you want mu to be minuscule. And then if mu is minuscule, you still ask yourself, well, maybe if mu is minuscule, then for this conclusion step here, I can do better as just testing against any of this. Because in the GLN example, we only tested basically the standard representation and its U and the determinant. Okay, which is much less than just testing all fundamental representations. Okay, but in case mu is minuscule, you can just classify what chi you have to test for this implication to hold. And if you do this, you exactly end up with the representations you see in the local model picture. So for minuscule mu, a refinement of that corollary produces exactly the conditions from the local model literature. Thanks. Thank you very much. More questions?
Can I ask something? It's maybe very stupid, but while I was in many works of similar flavor, for example, when in functional sort of files, there's this assumption of G that being simply connected, and this fundamental group being torsion free. And for the life of me, I cannot understand why we need this to be torsion free, this fundamental group. I mean, in general, and this was, if I'm not mistaken, an assumption you made as well.
Right. I mean, the derived group to be simply connected, and for this type of stuff is simply to have enough representations of G.
Yes.
Otherwise, you have less representations and maybe not enough. And for this torsion freeness of the group, it just if you don't ask, examples where it fails are ramified anisotropic tori. Like you take a ramified KOTP, a ramified quadratic extension, and then you look at the restriction of scalars. Well, should do it integral units of GM. You have a norm map down to GM again, and you look at the kernel of this norm map. Okay. I don't know. This is an anisotropic ramified one-dimensional torus, and if in this context, if you don't ask this torsion freeness condition, you will get counterexamples to the conjecture there. But
the way I understand is that, but maybe I'm wrong. So if you don't have this fundamental group to be free, then you have some non-trivial stabilizers. So I mean, you have a finite sum, right? So in that case, you not expect to have some moduli spaces because you have the non-trivial addition on the finite, right? So that's what happens in the modular curve case always. In that case, the fundamental group is some gamma 0, and you want, or gamma 1 or gamma, and you want to avoid torsion. Yes. If you have torsion, then this thing will never be a module space. So that's the connection. Don't think so?
Maybe, I don't know. I mean, here this fundamental group is really the algebraic fundamental group of G, so, but yeah, and
if you take the profinite completion and then you have finite things, then this thing is still the I mean,
but it's of G, not of the moduli curve.
Yeah. I mean that would be. I mean that maybe I'm wrong. So
I don't know. Maybe you're right, but I don't get it. But I would be interested if you.
But explain maybe later. I only know this thing. So
yeah. Okay. But did you have another?
Yeah. So. Maybe I'm not able to formulate this correctly, but in practice, what we do is moduli space for certain representations of G equipped with certain filtration. So maybe that's not the option. So it's a kind of concatenation of the generous maps. So, yeah. I understand that in the modular case, this is the map coming from the Durand homology. So in this case, I suppose you have an abstract version of this. But the question is, can you make a connection with the moduli? I mean, moduli space mean to me any point as an interpretation in terms of I don't know the algebras, some integration or I mean,
it's a good point.
Or something. So I was expecting to have some interpretation in terms of the invisible groups or something like this.
Yeah, that's a good question. So what, I mean, usually whenever you have a moduli description of the local model, you somehow write down the same conditions in terms of moduli of abelian varieties, and you end up with a moduli interpretation integral one of the Schumann variety. This is how it's supposed to be. Of course, the hope here would be to, in the end, translate it back to the Schmor variety. This one has to do something, because here we, in writing it down, we really use that the formation of these Grassmannians are functorial in the group. And you just, for Schmor varieties, you don't have a theory of Schmor varieties, which is functorial under any representation in particular. And it doesn't translate one-to-one. But you could still, the best I could imagine is that you somehow you can get a moduli interpretation in these terms whenever you can test when you have enough representations such that your Hodge co-character stays minuscule.
Yes.
But so I'm not sure that this picture here, what is nice is that it gives an explanation for these conditions. But what is problematic is that I'm not sure that in exceptional cases it brings you closer to a moduli.
Yeah. Rather, but you try to. So you take a Shimura curve over top of your field bigger than, and it's not PEFI, but it's very close. Yeah. So in that case, you have a kind of interpretation those in terms of the algebras of some formal rules, because you still have, I mean, I'm talking about the Shimura variety over C, so. But over QP or FP, transition of stability of the prime, you still have interpretation in terms of both things similar to that and formal groups. So in that case, maybe you may have parallel.
Maybe I don't know.
It would be interesting because this is not the that. So
Maybe.
thank you.
Okay.
Okay.
Thank you.
Any more questions? Well, let's continue.